question paper. So I'm going to use that formula. Get e to the minus t a cos 2t plus b sine 2t. Okay, this is called the homogeneous solution. Okay, good. Now what you have to do is you have to go back to the original problem. So the original problem as written down there has infinitely many solutions, and the theory says solve it equal to 0, which we've done, and find one more solution, add them together, and that's all the solutions. The infiniteness of the solutions is captured in the homogeneous. So now we're back looking at y double dash of t plus 2 times y dashed of t plus 5 times y of t, and it's equal to a constant 12. Now you look back, what you have to do is you're going to try, you're looking for a solution. So you just need one solution. So what you're going to do is you're going to start chancing your arm. And these things that we're doing are called ansatz, that are trial solutions. And we would have discussed this in depth, that what you have to do is try a solution that looks like this. And this is a constant, so what we should try is try a constant. So our trial solution is a constant. And we're going to try and force that constant into solving this. Now, if we're going to force this into this, we have to calculate the derivative, and luckily this one's quite easy because the derivative of a constant is 0, and then the second derivative of a constant is definitely 0. So now force this data into this differential equation. The second derivative is 0 plus 5 times or 2 times the first derivative is 0 plus 5 times the trial solution itself, which is c, and you're trying to force this equal to 12. And luckily this one isn't too difficult because you're just trying to force 5c to be equal to 12. All you have to do is divide both sides by 5 and find that c is equal to 12 fifths. So if the trial solution is the constant function 12 fifths, it is a solution of the differential equation, and therefore we can write down the general solution. The general solution is adding the homogeneous plus the particular. Didn't think I'd fit it in. Oh, very good. Okay. Homogeneous plus particular. And that's part A done. Have we answered the question I was asked? Find, using the method of undetermined coefficients, the general solution. I've found the general solution. Does the answer make sense? You can have a think about this. Yeah, because if this is a damped harmonic oscillator, the spring force is quite big, and that means that it's underdamped and you're getting oscillations. And then the constant external force, like someone pushing it, and eventually as time gets big, there's oscillations, but they're getting smaller. You're left just with the door being, or the spring, or the door, or whatever, just being held open at a constant distance. Right, so that's part A. Part B goes up to here, does the same thing, but then what you want to do is go off and find A and B. So this is the general solution for no matter what the initial conditions are. In question B, you'd be given initial conditions. Okay, so we'll take exactly the same steps. First, we solve it equal to 0. So this one is x double dashed of t plus 3 x dashed of t plus 2 times x of t equal to 0. So first solve it equal to 0. How do you solve this? You do r squared plus 3r plus 2 is equal to 0. This one, okay, at this stage factor, you can use the minus b formula, you can factorize it, it doesn't matter. If you do it, you will get, I'm quite confident you'll get r is equal to minus 1 or minus 2. So you can use the minus b form, you can factorize this r plus 1, r plus 2. So r plus 1 is equal to 0, r plus 2 is equal to 0. That means that we have a homogeneous solution. There are two different real roots, so there's two exponentials, some constant times e to the minus 1t plus some constant e to the minus 2t. And the form of the solutions between Laplace and this, they should start to make sense. So like you start to see this pattern of the two exponentials, and you know that, for example, if this is a damped harmonic oscillator, it is that this one is overdamped. Because there's two exponentials. If you think about it, it closes fast, then slow, it's overdamped. Right, what's the next thing? Then we go back to the original question, which was x double dashed of t plus 3x dashed of t plus 2x of t equal to now 2t. Now we have to kind of recognize, and there's a table kind of suggesting what you need to try. If you try a multiple of t, it's not going to quite cut it. You have to recognize this is like an mx plus c. It's a line, so we need to try a line. It's probably a good exercise to go through all the questions. If you look into the chapter 2, you'll see that there's some hints to the questions. If you can say in advance, looking at the original equation, saying what the trial solution is going to be, in between the exercises, where the hint is given, the marking scheme and the examples, if you can do that, that's probably a good exercise. So in the manual, I think all the time, almost, the trial solution is given. You try and guess what it's going to be. So I read this, oh, it's going to be a constant. Read this. What is the line? It's going to be like mx plus c, ct plus t. So the trial solution here is ct plus d. I've written as well a something called a numbers program. So it's like an e-learning tool where you can practice your differentiation of these once you know how to pick your trial solution right every single time. So go back here, we're going to try and force this into this. So we should find the first derivative. So the derivative, okay, so fix the c. The derivative of t respect to t is 1 plus the derivative of constant d is 0. This is just c. And then if we differentiate that again, the derivative of a constant is 0. So we're going to try and force that data into this differential equation. So if we try and force it in, second derivative is 0, plus 3 times first derivative is c, plus twice what we're looking at, which is ct plus d, and we're trying to force this to equal 2t. This is just like up here. So try and force the trial solution to solve the original problem. Okay. So what we're going to do now is we're going to multiply out